Okay, got a few more people coming in. Great. Hi, everybody. I miss seeing everyone in person. This is going to be a really weird end of semester, but we're doing it. I feel like we have a good plan. So here's where we're at. So quiz 3, I explained this to you last time, but I want to make sure everyone knows. I've decided it's going to be the same format as your previous quizzes, so 25 short answer questions. The formula sheet is already up on Moodle, so you can take a look at that. Now you have all the formulas in front of you because it's going to be open notes, open book. I'm going to say I discourage open internet, but I'm not going to stop you if Googling something helps you figure out a question. But I will say that you're going to hand it in on Turnitin on Moodle, so it checks against internet sources, so no plagiarizing, copying, pasting from internet sources. And since all stats teachers teach a little differently, you can get something wrong if you're not saying it the way that I've been teaching you to say it. So like when I ask you to conclude something, when I give you a p-value and a confidence level, I want you to say you either reject the null hypothesis or you fail to reject the null hypothesis. And other people might say that a little bit differently. So just make sure that you're answering it kind of the way that we've been doing all semester. So it'll be uploaded as just a Word document on Thursday at noon, and it's due Friday at midnight. It's really not supposed to be a time race. We're not going to have lecture on Thursday, and I really expect that you could get it done during that normal class session, 12:30 to 2:10. If you're prepared. If you're not prepared, it might take you a little bit longer to hunt down all the answers. If that's not enough time, email me now if you think you want an extension. I'm not meaning to make anyone miserable trying to get this done. If your living situation is crazy or something, just email me and I can give you more time on it. I'm more keeping the deadline so that people don't put it off forever. I'd rather it all get done on Friday because next week is spring break. I'm sure everyone has really exciting travel plans. So at least you should take a little bit of mental break from some of your classes because it's been a weird time transitioning to all of this. So it's not a group quiz. I really want you to work on it alone and it to be your answers, but you have everything else to kind of help you through it at this point. Anyone have any questions about that? Okay, so getting yourself ready for quiz 3. How to review, I would focus on getting your notes organized. So making yourself a study guide like I talked about last time for each test that kind of goes over why you use the test, what the null hypothesis is, how you use the critical value, how you get degrees of freedom, that type of thing. If there's anything in particular that's confusing or you want me to go over, you can set up a meeting with me or Jermaine on Zoom so that we could just go over things. Again, we're going to spend some time in this class going over stuff. But remember that after Thursday at noon, so basically when the exam gets posted, Jermaine and I both won't be answering any stats related questions. I'll answer questions if you don't understand the wording of a specific question. You can email me that, but I'm not going to be explaining to you, what a paired t-test is at that point, because that's when you're supposed to kind of know what you're doing enough to be able to take this quiz. No questions? Okay, sounds like more and more people are coming in. Okay, so today we're going to go over non-parametric methods, and then we're going to spend some time reviewing for that quiz. I guess I didn't write it in here, but there's no lecture on Thursday. I'll make sure I send that out in an announcement, because instead you're just basically going to be taking the quiz. And there's no problem set due this week. There is a review sheet similar to the last one posted on Moodle that I think you should take time to go over and make sure you're asking questions if you have any questions about any of those issues. Because things are a little different and this is now going to be open note, I decided that I want to be able to ask you questions about any of the tests that we have covered so far. So even though last quiz had t-tests and chi-squared on it, I'm going to re-ask those questions potentially on this quiz. So make sure you reviewed everything that's on that review sheet. So confidence intervals and p-values aren't going away. Hypothesis testing isn't going away. And then still the questions on t-test and chi-squared and all that could come up again on this quiz. But this is the end of new content, and it's not really, especially now that you guys don't have to memorize this, this is not a super difficult chapter. So I think it's only going to take about half the lecture, and then we'll move on to a review activity. So anyone need me to stop? I can see the chat if you have questions, so just click in there. Okay, so non-parametric tests. We've been talking about all the tests that we've gone over so far, for the most part, in one of their assumptions said you had to be normally distributed. Your underlying data had to be normally distributed. So this whole group of tests are all the ones that don't rely on the assumption that your samples come from a population that's normally distributed. So I kind of have been alluding to the fact that these exist, and now we're going to kind of go over basically what they are. There's, for the most part, a counterpart test that's non-parametric for every parametric test that we've already learned. But the idea behind this, and we'll get into it a little bit more, is not that it's not perfectly normal or something like that. This is to deal with populations that are truly not normally distributed, like bimodal or trimodal or uniform distributions. That's what these are meant to deal with. We'll talk more about something that's close to normally distributed and what we do with that kind of at the end of the lecture. But think about these really crazy kind of distributions, and you would never think that it was normally distributed, and you wouldn't want to use one of our parametric tests on it. So non-parametric alternatives exist for all the tests we've learned so far, except for linear regression. Are they better? Are they worse? My feeling is they're kind of like the hashtag nailed it, which is now a TV show. They probably taste just as good, but they lose something in the presentation. So this is a good example of nailed it. So they're kind of getting you the same answer as a parametric test would, but they're not nearly as strong or robust in some ways. So you have to be really careful if you want to decide to use them. It's not just that if you think your data is a little bit non-normal, you're going to immediately switch to a non-parametric test, because you are losing something by switching to these tests. So importantly, before we start talking about these, can data be non-parametric? No. We're talking about data is either normal or non-normal, Gaussian or non-Gaussian, but the tests are either parametric or non-parametric. It's just kind of a semantic thing that you have to remember. Your data is either normal or non-normal, and your test is either parametric or non-parametric. So what do non-parametric tests do? Most are based on the simple concept of putting your data in rank order. So instead of looking at all of your data points the way we have so far, they would just put them as first, second, third, fourth, fifth, sixth, put them in rank order, and then do all the tests on them that way. This would ensure that the test is not affected by outliers, right? It's the same thing as taking a median, where you don't care if your highest value is really far away from the rest, because it's just going to be your last value, and they kind of go in rank order from there. And because it doesn't, it just puts them in rank order, they don't assume any particular distribution of the data. So that's how we can get away from that assumption of normality. So there's still assumptions, right? You still have to worry about certain things in doing these tests. The first one is on every single test that we do, right? The data are randomly sampled or representative of the population. If you violate that assumption from the beginning, you're screwed. You can't do these tests because you just collected your data poorly. Each value is obtained independently. They can't be linked in some way. But those are the main two assumptions now. Now we don't have that it has to be a underlying normal distribution. We don't have that the standard deviations have to be equal, or all the other ones that we put on the other tests. So now we just have to be having sampled correctly, and then we can move forward with these non-parametric tests. So non-parametric tests can help correct skewed data. That's one of the things that they can do. So remember skew, like this is positively skewed or right skewed, negatively skewed or left skewed. If you have something that's positively skewed, what can you do? Does anyone remember what we do if we have right skewed data? It's from very early in the semester that we talked about how you could deal with right skewed data. Can't see who that is. Tiffany, you want to try? Can you unmute yourself?
Don't you just log transform it?
Yeah, exactly. You can log transform it. So log transforming, we talked about, is going to basically change everything so that it ends up looking normally distributed. It brings the right side kind of in a little bit and lengthens out the left side so that we have something that ends up being normally distributed. If you had something that was negatively skewed or left skewed, so the tail is on the left side here, log transformation is going to make that skew worse, right? We said that log transforming only worked on right skewed data. If you were to do that to left skewed data, you just kind of make the problem worse. So this is the type of thing that if you have super left skewed data, you can't go that log transformation option and you're going to convert it to ranks and do some sort of nonparametric test on it. In general, the feeling is that you should be, if you can log transform, so if you have right skewed data and you can log transform and then use a parametric test, you should do that. That's the better option than using a non-parametric test. So if we're comparing two unpaired groups, does anyone remember what test that would be in that we've already learned, a parametric test, comparing two unpaired groups? Pat?
Would it be the unpaired t-test?
Yep, so the unpaired t-test or the independent samples t-test or the students t-test, it had all those names, right?
Good. To anybody else, like, it's good, it's good.
I gotta mute somebody. I don't know what that was. That was exciting. Okay, so I can't lower everybody's hand. So right, that's the two sample independent t-test or students t-test or unpaired t-test. The non-parametric counterpart is called the Mann-Whitney test, and this is doing exactly the same thing except for that it converts them to ranks first. So it's sometimes called the Wilcoxon rank sum test. It kind of has these two names. It converts the data to ranks and then gets the mean rank of each group. The null hypothesis for this is that the distribution of ranks is totally random. There's no difference in mean rank of each group. So again, your null is going to be that there's no difference. Your alternative is that there is a difference in mean rank of each group. Other than that, it's going to give you the same exact output that a unpaired t-test would do. It's going to give you a p-value, right? And then you're going to interpret the p-value. So we're not even going to do these by hand. This can just be done in R when we get to it. But if you got a p-value that, if you set your alpha equal to 0.05 and you got a p-value of 0.01, what would you conclude in this for this test? So you set your alpha equal to 0.05 and you got a p-value of 0.01. What's your conclusion? Zach, go ahead.
You reject the null.
You reject the null, which means there is a difference in mean rank of each group. So it's just saying that there's a difference between these two groups. Good. And so the same thing, if it's greater than 0.05, you're going to fail to reject your null, and there is no difference between the two groups. So really simple, right? We just have to remember that these alternatives exist. That's what we're talking about. Comparing two paired groups. What is the parametric test that can compare two paired groups? Alex, is that you raising your hand? Unmute yourself.
Okay, I might be wrong. The chi-square test?
Nope, this one is almost too simple. This is two paired groups, and the name of it is like you're gonna kick yourself when you hear the name of it. You don't remember?
Paired t-test?
Yeah, yeah.
Okay.
Yeah, it's the paired t-test.
I'm kicking myself right now.
Yeah, it was too simple. So the parametric counterpart for this one is the paired t-test. The nonparametric counterpart is called the Wilcoxon matched pair signed rank test. Annoyingly, Wilcoxon did a lot of work, so we called this one the Wilcoxon test, not to be confused with the previous one, which is also called the Wilcoxon summed rank test. So that's why I'll probably refer mostly to the unpaired group as the Mann-Whitney-U and this one as Wilcoxon's test. So that's it, right? If you had two paired groups that are not normally distributed, you're going to use this test. So correlating two variables, the parametric counterpart, we didn't really give it a name when we went over it, but it's called Pearson's correlation. The non-parametric equivalent of this is called Spearman's rank correlation. So another way that they're putting things in rank order and then trying to correlate them. It has the same assumptions as Pearson's correlation, so it needs to be a random sample. The samples are paired, you're sampling from one population, observations are independent, X values are not used to compute Y values, X values are not experimentally controlled, there's no outliers. But the big difference from Pearson's is that it does not assume that there has to be a Gaussian or a normal distribution underlying it. It also does not assume a linear relationship, which is really nice because we talked mostly about linear regression and linear correlation. Now we can use this for working on things that we know are correlated, but they're not correlated linearly. Okay, so, and I remember at the beginning I said that there is no non-parametric counterpart to linear regression, which is a failing of it. So does anyone remember the difference between linear regression and correlation? It's a little bit more difficult. That was when we were still meeting in person. I got to see all of you guys. The difference between correlation and linear regression. No one? Eric, go ahead. Unmute.
Hi, can you hear me?
Yeah.
Okay, so if I remember correctly, a correlation is just two variables that are occurring together, and you find that like one increases not because of the other, but just at the same time.
Mm-hmm.
Whereas a linear regression is trying to identify a causal relationship and use one to predict the other.
Yes, so that's where it really matters that we set X as your experimentally controlled or your independent variable, and then it predicts what you're expecting to get from Y. Correlation doesn't matter which one's X and which one's Y. You can swap them easily. Regression says X is being used to predict Y, so it matters which one they go to. So we said in regression, we're going to fit a line through it. That's kind of what we're doing. Correlation, we're just saying, are these two correlated? Good. So same thing here. We can have the nonparametric counterpart to correlation, but we don't have a nonparametric counterpart to linear regression. So if you want to use this you want to use your X to predict your Y and you don't have normally distributed data, you've got to go to a whole different field of statistics or work on nonlinear regressions. Okay, so comparing three or more groups, the means of three or more groups, which test would that be? Andre? Say it again.
ANOVA.
Yes, wait, who's saying that? Eugen?
Yeah.
Okay, good, yeah, but this isn't ANOVA. Andre, I hope that's what you were gonna say too. The parametric counterpart is a one-way ANOVA, which we talked about last time. The non-parametric version of this is called the Kruskal-Wallis test. I'm kind of going over these fast because they're literally, you just got to remember that these exist. When we're actually doing this in R, you will get to see kind of how it plays out. But at this point, I just kind of want you to be aware that the non-parametric counterparts exist. So paired samples in three or more groups. Does anyone remember what that was called in our parametric test? So they were paired, but you had three or more different groups of them. Eric, go ahead.
That's the repeated measures ANOVA, right?
Yeah, repeated measures ANOVA, which we said was similar to a paired t-test, but now you could have more than 2 groups. That was a repeated measures ANOVA. The non-parametric counterpart to this is called Friedman's test. Does the same thing, but without assuming a normal distribution. Okay, so that's kind of the quick overview that they exist, right? So why wouldn't we just always use non-parametric tests, right? So we're saying we've gone through all of this work of trying to figure out if something normally distributed or not, and we had this option all along to just use a test that didn't assume normality. Why wouldn't we just use them to begin with? The main reason is that non-parametric tests are less powerful when the data are not Gaussian. So really large samples where you've increased your power because you have really large samples work fine with non-parametric tests, but we're talking about thousands and millions of them. But most ecological data that we're going to be collecting, you lose your ability to detect differences if you use a non-parametric test. So unless you're really, really sure the underlying data is not normal, you're going to try to default to that parametric test in most cases for the data that you're using. Because you're probably not working with huge sample sizes where this happens. You do see it a lot, I would say more in like biomedical journals where they do have really huge sample sizes and really non-normal data, and so they'll use some of these tests and they work just fine. But remember, like, they are meant to be with non-normal data, but they're just less powerful in general. Non-parametric tests are usually not reported with confidence intervals, and we talk a lot about confidence intervals in this class as a really good way of illustrating where our differences are and the magnitude of the differences. Sorry, I realized my microphone was hidden in my hair. And again, like I said, non-parametric tests are not readily extended to regression, so that's kind of an issue, a downfall of them. So to use or not to use, here's kind of a breakdown of what you can think of. So if your distribution is Gaussian, so it is normally distributed. Can you guys see my pointer when I do this? No.
Yeah, we can.
Oh, it can? Oh, there's something called a spotlight. Ooh, that's nice. Okay, cool. So if your distribution is Gaussian, which means it's normally distributed, but you choose to do a non-parametric test, if you have a large sample, you're probably fine, right? If you have a huge sample, a non-parametric test is going to give you the same result. You're perfectly fine. But if you have a small sample, this can be really misleading because your non-parametric tests have little power with small sample sizes. Now, if your distribution was non-Gaussian, so it wasn't normally distributed, and then you ended up using a parametric test and you had a large sample, again, you're probably okay. So we'll probably talk about that. If you have a big sample size, but your data doesn't look perfectly normally distributed, we'll probably say, okay, but if you have a large sample size, let's go ahead with our parametric test. But if you have a really small sample, parametric tests are not very robust to violations of normality. So if you, basically, you're screwed if you have small samples and you choose the wrong test, right? So if you have a really small sample, you really need to be careful to know that your underlying distribution is normal or not normal and choose the correct test. Large samples, it doesn't matter quite as much for. And this is something to kind of critique other people too. If they've decided to use a parametric test and they haven't proven to you that they have normally distributed data, you'd be like, well, your sample size is small, so you might be misleading your reader. In each of these, right, so we could have 4 here where if you had a Gaussian distribution and you chose a parametric test, they'd be fine for both of these. If you had a non-Gaussian distribution and you chose a non-parametric test, they'd be fine for both of these, right? That's kind of how this works. Okay, so going back to what we learned kind of in the beginning, we talked about normality tests, right? So should you use a normality test to figure out whether you should use a non-parametric or parametric test? Again, if you have a large sample size, normality tests can be very helpful because basically, like, they do a good job of testing for normality. If you have a small sample size, they're not necessarily that helpful. So over and over again, it's like small sample sizes, you're kind of screwed and you have to be really careful. And in biology, we use a lot of small sample sizes. So that's why in the end, you're probably, as long as you can assume the population has a normal distribution, you're probably going to end up using a parametric test. So overall, the pairs of tests are unpaired goes with Mann-Whitney, paired goes with Wilcoxon, ANOVA goes with Kruskal-Wallis, repeated measures ANOVA is Friedman's, and Pearson's correlation is Spearman's correlation. So I've come up with this kind of overview of all the different tests. I think it might look a little confusing at first glance, but I think you'll actually get it pretty easily. So this is what kind of test at the top here. If we want to use one variable to predict another, and the data is normally distributed, what test would we use to do this? So we want to predict one variable from the other, and it's normally distributed. What test? Andre?
I'm gonna go out on a limb since I'm still rusty with all this, but oh wait, oh, this is from the very beginning of the semester, isn't it?
No, this was right before we went online.
I was gonna say, is it a unpaired t-test? No.
Alex, what do you think?
Is this one the chi-square test?
No.
No, darn it.
I know.
Oh, so confident.
Zach, you want to try?
Is it linear regression?
Yeah, linear regression. And it should have been kind of a key for you because it's the only one that doesn't have the no normally distributed counterpart, right? That's what we're talking about here. And to be fair, chi-squared tests aren't in this diagram at all because they kind of are their own separate thing. I'm not going to add them in. I think it would just make it more confusing. But at this point, don't worry about putting that on here. So what I want you guys to do, good, it's only 1 o'clock. Everyone go on Moodle, and this blank sheet is kind of uploaded onto Moodle. And I want you to try to figure out if you can fill it in on your own. So you should be able to do it on your computer. Take 5 minutes, 10 minutes, and then we'll reconvene. So keep your speakers on, get that downloaded, and just look it over and see if you can fill in any of these on your own. I think I'm gonna, for people listening online, I'm gonna stop the recording here, but everything will be posted later. It's just gonna be a lot of